Howdy folks, we've already seen this particular version of the formula for a tangent plane where we express our surface as the level curve of some function of three variables. We then, as long as the gradient is in 0, compute that gradient and dot that with this vector right here. Just as a reminder, this vector right here is a collection of vectors, all of whom have their tail at a certain point. The point ABC, which is a point that's going to be on the plane. So we want to go ahead and construct this formula. We've seen it already, we've worked with it already, but let's see where this formula comes from. So if we jump back up to here, in this problem here we're asked to consider the surface f of xy equals 0, assuming it's differentiable at the point ABC with the non-zero gradient. Let's give the equation a tangent plane. So the picture, what we have in mind here is we've got some surface, and while we might express this surface, we may be able to express this surface as some z equals f of xy. What I really want to do is construct this function f of xyz and set it equal to 0. So if you're given a function in this form, to construct it that way, you would just subtract one of these two over the other side, and that would be your function. So for example, if I were to subtract over the f of xy, I would have this, and this is what I would use as my f of xyz. So we've got this surface in 3 space. I guess let's give it a little bit of orientation here. And what we want to do is we're going to pick an arbitrary curve passing through the point ABC. So let's put our point ABC on there. Maybe that's the point right there. Let's try to keep my labels out of the way. So A, B, C. There's that point that we're given, and we're assuming the function's differentiable there. So let's pick an arbitrary curve. Pick an arbitrary curve passing through, let me say this, on the surface, passing through the point ABC. Then we're going to assume that we can parameterize that curve, so let's let R of t be its parameterization. So what I'm saying here, folks, is we've got some curve that's on this surface, and it passes through this point right here. This is what I'm using as this R of t. By the way, I could have picked some other R of t. Maybe this could have been my R of t instead. So maybe this is, another R of t. So maybe we'll call it R2 of t. So I could have picked any curve. This is an arbitrary curve passing through the surface. So as a reminder, this function, f of xyz, is a function whose graph lives in R4, but we are just looking at a level surface of it. If we want to describe the graph of this particular parameterization R of t, where it lands on the graph of f of xyz, we could just go ahead and say that we have the function f of r of t, and that would then be equal to 0 because we're on this level surface of the graph of that function. So if you're having a hard time thinking about that, folks, if you think about maybe f as outputting the temperature at any point in space, so you plug in the point in space that you're at and f outputs the temperature, what we could do is if we have this R of t, which gives us a collection of points as we move through the values of t, this f of rt then would give you the temperature at any point as you move along this line, as opposed to giving you, if we were just looking at f of xyz, the temperature at any point on the entire surface. So now what can we do? Well, this is a parameterization, which means we could write it as f of x of t, y of t, z of t. Even though we don't know what those 3 coordinate functions are, it's a parameterization of the curve, so they must have those 3 coordinate functions. And now we need to do some differentiation. And this is in fact a trick that we've seen a couple of times. But let's go ahead and look at the graph of f, or look at the function f. And at first we thought of f as having these 3 independent variables, f of x, y, and z. You plug in the point in space, and it outputs the temperature. But then we introduced this notion of a parameterization to it as we looked at a specific curve. So now what we can do is we can input a specific point in time, and that tells us what point on the curve we're on, and then when we plug that point into the function, we'll know the temperature, if you're following that analogy. But regardless of what analogy we're using, I'd like to differentiate both sides with respect to time, which is the independent variable as this has been written, when we take our function f and we restrict ourselves to the curve r of t in that domain. So if we go ahead and differentiate following the chain rule, we would have, for this, we would have partial f partial x dx dt plus, and I'll finish it out. So folks, this is what this came out to be. And remember, we've seen this trick a few times. I color-coded it to help us see it a little bit easier. But notice that these three factors right here are just the gradient of f. And it's as if we're dotting it with this right here, which would be the vector dx dt, dy dt, dz dt, and that's just our r prime of t. Folks, I've actually kind of done some extra work here. We already knew this from some of the earlier work that we've done. We already knew that this is what was going to happen. Why did we know that was going to happen? Well, the gradient is always orthogonal to, if we're doing with a 2D gradient, it's always orthogonal to a level curve. But here we are with a 3D function, meaning that the gradient is always orthogonal to a level surface. So what I'm saying there is at any point, if you were to compute the gradient vector is always orthogonal to that level surface. So at our particular point, this would be the gradient. That's getting a little bit messy now. That's the gradient of f of a, b, c, and it's orthogonal to that surface, which is what we're trying to show here as we're building this equation of the tangent plane, because the tangent plane is the collection of all of the tangent vectors of all of the curves that could possibly pass through this point. So of all these different r of t's here, I've got two of them, a blue one and an orange one, passing through the point ABC, but they each have their tangent vectors, and what we're trying to construct is a plane that contains all of those tangent vectors. And notice here is a tangent vector to an arbitrary curve passing through our point, and here is some vector that's orthogonal to that arbitrary tangent vector. So this is why the gradient vector is going to serve as our normal vector to this tangent plane. But let's just finish spelling it out. We know that at some t equals t naught, because this curve r of t, how did we choose it? We chose it to lie on the surface. That was part of it. It had to lie on the surface, but it also had to pass through the point ABC. So at some t equals t naught, r of t naught gives us the vector ABC, meaning we can think of it as passing through the point ABC. And so that means r prime of t is a vector of the form, or can be written as a vector in the form x minus a, y minus b, and z minus c, because we usually think of the tangent vectors, when we transcribe them, we think of them as having a tail at the point where the tangent line comes off. So I don't have a tangent line on here for my curve, but maybe this would be my tangent line. And we always, even though the vector could be thought of as living anywhere, that same vector could be thought of living anywhere in the vector space, we usually anchor it so its tail is at that point there. And the key thing is that it would have the magnitude of whatever r prime of t is, and the direction is what we're after here. But we can always think of it as having a tail at the point ABC. So that means we can write this vector in the form x minus a, y minus b, z minus c. But the other thing we already know about it is, since it's from r prime of t, it's going to be orthogonal to the gradient vector. So we're done. We have the gradient of f. When we dot it with this arbitrary tangent vector, x minus a, y minus b, z minus c, that has to come out to be 0, and remember that's how we defined a plane. That is, this is the plane containing any non-zero tangent vector to any smooth curve passing through it. So this is a plane containing any non-zero tangent vector of any smooth curve. R of t is how we're writing them, passing through the point ABC. So on the surface, passing through the point ABC, which is what we were after. So folks, that's how we get this definition of the tangent plane. I hope that helps. Let me know if you have any questions.